So in this video, we will discuss about recurrence relation. So recurrence relation is a relation that is used to represent a recursive function. So I hope everyone knows about recursive function. So just we can recall that the recursive function is a function. So that calls the same function again and again. So the function is called by itself again and again, and that repeated function calls should end with one stopping criteria. So this is the recursive function. So, so the recurrence relations are used to represent these recursive functions. So we will see one simple example for this recursive function. So this is a recursive function, that function fun. So in this function, this particular line, so this is a recursive call. So initially that function take one argument, that is n. So and then inside that function, so each iteration the n value will be reduced by 1, and again with that new value n minus 1, that function is called again. So actually, the output of this function is initially it will first print the value n, and then the next iteration it will print value n minus 1, and then n minus 2, so on. So the stopping criteria for calling this function is defined in this condition. So this recursive function call will be happen until the n value is greater than 0. So for example, if n equal to 3, suppose if n equal to 3 means, so in the first iteration it will check 3 greater than 0, and then it will print 3. So and then the same function will be called with value 2. So again the same function will be executed. So 2 is greater than 0, so it will print 2. Then again it will call with same function will be called with 2 minus 1, 1. So again the same function executed, 1 is greater than 0, so it will print 1. So and then it will call function n minus 1, that means 1 minus 1, 0. So when the function is called with the value 0, that condition will false, so this function call terminates. So now, so in the last video we saw about how to measure the time complexity of a function or of any program using count method. Suppose if you use the same count method for calculating this, so measuring the time complexity of this program. So recall that for in the count method, we need to count the number of operations inside that function, and then we need to find the frequency, that the number of times that operation is executed. So here this operation, so inside this function, this operation will be executed for one time. So and it will be executed for a unit times, so 1 into 1. So we take for the simplicity we take the unit time as 1. So the time needed to execute this function is 1. So this print is also a simple function, so it will be executed for one time, and then the time taken is 1 unit, so 1. But this fun n minus 1, so we cannot able to determine the time needed to complete this particular function. Also we don't know how many times that particular function will be executed. So this is unknown. So that means the number of time. So how many number of times this particular function will be executed, this is unknown. So these kind of recursive functions, so line count method, a count method cannot be used applied to measure the time complexity. Then how it can be done? So So there are two methods by which this particular complexity can be evaluated. So first one is by using tree method. So tree method. So this function call can be represented in a tree structure. So before that, so for any kind of recursive function, so first we need to form a recurrence relation. The recurrence relation actually is used to find the time complexity of that particular function. Suppose the recurrence relation is can be represented by t of n. So this t of n is actually the overall time that is taken by this entire function. So this n represent the actual input size. So this d of n. So this d of n actually represent the time taken by that particular recursive function with the input size n. So now suppose this particular statement, so it is not a recursive call. So it takes one unit time, and this print is also it also taken one unit time. So now this is also a function call. This function call, this function call calls the same function fun, but here the size of that input is n minus 1. So we can assume that the time taken by this function is t of n minus 1. So now the overall time needed to complete this particular function is t of n, and inside that function there are two statements that will be executed by a unit time, and then one recursive function call, this function call with the different input size. So here the input size is n minus 1. So we can assume the time needed to complete that particular function is t of n minus 1. So now we can frame that recurrence relation. So t of n is equal to t of n minus 1. So sum of all these lines, sum of the time needed for all these lines. So t of n minus 1, and we can take both that two statements as a single time unit. So 1. Okay. So this is a simple recurrence relation. So now, how to find actual time complexity of this particular recursive function? So I already told you one method, that is tree method. So I will explain how this tree method is can be applied. So in the tree method, suppose if that n equal to 3. So the first function t of 3. So this t of 3. So inside that's t of 3, it will, when n equal to 3, so first it will print the value 3. So the print statement. So this print statement. So this print statement will print a value 3. So and then again the function call. So this function call. So this function call, now it will t of 2. So 3 minus 1, 2. So again, this t of 2 will get executed. So in this t of 2, first it will print 2. So again, it will call a function t of 1. So since 1 is greater than 0, so the if condition will true. So again, it will print 1. So and then that function t of 0 will be executed. So now when n equal to 0, that condition becomes false. So it terminates. So in each time the function calls, so the actual time the particular function call executes is, so for printing that particular statement, so print statement. So this take 1 unit time, and this take 1 unit time, and this take 1 unit time. So as a whole, this function call t of 3 takes 1 time unit times, and t of 2 takes 1 time unit, t of 1 takes 1 time unit, and t of 0. Though t of 0 doesn't print any value, but still when that n value is 0, this conditional statement will be executed. So one statement will be executed, and the time taken by that statement is 1 unit. So this also take 1 unit. So in total, so in total, it will takes 4 time units. So 4 units of time. So if that n value is 3, it takes 4 unit of time. So that means t of 3 equal to 4. So in the same way, if the n value is 4, it will takes 5 unit times. So in general, if that time taken by this particular recursive function t of n is n plus 1. So this is the time taken by this particular recursive function t of n is equal to n plus 1. So if we represent this in big O notation, so big O or big omega anything, so O of n equal to n. So this is the time complexity of this recursive function. This is derived by using a tree approach. So now one more approach is substitution method. So substitution method. So before going to this substitution method, so here I give a simple recursive function for this. That means d of n equal to t of n minus 1 plus 1. So actually, so this is t of n, and this takes 1 time, and this takes 1 time, and this is t of n minus 1. So by total, t of n equal to t of n minus 1 plus 1. Okay, so this recursive function is true if n value is greater than 0. So this is true if n value is greater than 0. Suppose if n value is 0, if the input value n is 0 means, so this particular if n equal to 0 means only this statement will be executed one, and these two statements will not be executed because this function will false. Okay, so these two statements will not be executed. So if n equal to 0, then the overall time needed is just this one. So 1 if n equal to 0. So this is the actual that full recursive relation for this particular program. So T of n equal to T of n minus 1 plus 1 if n is greater than 0. So T of n equal to 1 if n equal to 0. So why this is if n greater than 0 means, so this condition, this statement will be executed that takes one time unit, and this print statement will be executed that takes one time unit, and this function con will also be executed that takes t of n minus 1 time. So total t of n minus 1 plus 2. So that 2 can be, for our simplicity, we just use 1 instead of 2. So that is t of n minus 1 plus 1. So if n equal to 0 means only this if condition will be executed. So only one time unit, that function will be executed. It will take only one unit time. So just this is the actual full recursive relation for this particular program. So now how this recursive relation can be solved by using this substitution method. So actual recursive relation is t of n equal to t of n minus 1 plus 1 if n is greater than 0 and 1 if n equal to 0. So just remember this. This is the recursive function that we are going to solve by using this substitution method. So how to solve it? First take this n greater than 0 condition. So t of n equal to t of n minus 1 plus 1. Okay, so take this as step 1. Okay, so in this particular step, to solve the actual function t of n, we should know the value for this t of n minus 1. So we know the value of t of n is t of n minus 1 plus 1. So put n equal to n minus 1. So in this statement, put n equal to n minus 1. So t of n minus 1 equal to t of, instead of n, we need to put n minus 1. So t of n minus 1 plus 1. Okay, so this is t of n minus 2 plus 1. So now we know that t of n minus 1 value. So substitute the t of n minus 1 value in t of n. So in step 1. So that is, instead of t of n minus 1, this is t of n minus 2 plus 1. And then again there is 1 plus 1. So now this is, it is equal to t of n minus 2 plus 2. So this is now t of n is equal to t of n minus 2 plus 2. So take this as step 2. So again, still to solve this t of n value, we should know the value for this t of n minus 2. So the same, substitute n equal to n minus 2 in the value of t of n. So t of n minus 2 will be, so is equal to t of n minus 2 minus 1 plus 1. So now, so this is equal to t of n minus 3 plus 1. So substitute this here. So now t of n equal to, so instead of t of n minus 2, this is t of n minus 3 plus 1. And there is again in the step 2 there is plus 2. So now t of, so t of n equal to t of n minus 3 plus 3. So take this as step 3. So in the step 1, t of n equal to t of n minus 1 plus 1. So in the step 2, t of n equal to t of n minus 2 plus 2. So in the step 3, t of n equal to t of n minus 3 plus 3. So we need to stop this substitution at one particular time. So just we take after step k. So in the step 2, t of n equal to t of n minus 2 plus 2. In the step 3, t of n equal to t of n minus 3 plus 3. So it follows one pattern. So if you, so if it follows the same pattern after the kth step, so the t of n value will be like this. So t of n equal to t of n minus k plus k. So this will be after step k. Okay. So now in the recurrence relation, so in the recurrence relation, the only value for t of n, we know the only value for t of n is equal to 1. So when it gives the value 1, so when that n is equal to 0. So the only value that is known for t of n is equal to 1, where n equal to 0. So we need to, so in order to solve this uh, equation, so t of n equal to t of n minus k plus k, we need to make this t of n minus k equal to t of 0. So when we can make, how to make n minus t of n minus k equal to t of 0 means if n minus k equal to 0. So when you solve this, it will give k equal to n. So now substitute this k equal to n in this particular equation. So in this equation, wherever there is k, just substitute n. So now t of n equal to t of n minus n plus n. So it is equal to t of 0 plus n. So now it gives t of n equal to t of 0 plus n, and we know, so t of 0. So from this recurrence relation, so t of 0, if n equal to 0, then t of 0 is equal to 1. So substitute that value here. So now it becomes 1 plus n. So now t of n equal to n plus 1. So that recursive relation, now t of n equal to n plus 1. So the same thing that we have get using that tree method. So in the tree method also we get the same thing. So t of n equal to n plus 1. So here the tree method also we get the same value t of n equal to n plus 1. So here in the substitution method also we got the same value t of n equal to n plus 1. So when you represent it using big O notation, so this can be represented as O of n. So this is the time complexity of this particular recursive function. So the recurrence relation is actually a relation that is used to represent a recursive function. So the the actual objective of this recurrence relation is to calculate the time complexity of a recursive function, because the recursive function time complexity cannot be measured using the traditional line count approach. So first, we need to find the recurrence relation for that recursive function, and by using that recurrence relation, you can either substitute the tree method or substitution method to calculate the actual time complexity of this function. So in the next video, we will see some more recurrence relations, how to solve that recurrence relation by using the same substitute method. Thank you.